So hi all, I am Narayanan PP, a research scholar from IIT Palakkad from India. So I'll be presenting one of my research work that is a novel capacitance-to-time converter for differential-type capacitive sensor insensitive to offset mismatch and parasitic capacitance. So before coming to the topic, let me just give an overview of the capacitive sensors. So basically, a capacitive sensor is a variable capacitor which hosts capacitance changes with respect to the measurand. So there are a variety of capacitive sensors are available. So differential type capacitive sensors is one among them. So it basically consists of two capacitors, say 𝐶01 and 𝐶02, and the capacitance of this capacitive sensor, means 𝐶01 and 𝐶02, changes differentially in presence of this measurand. That is like if there is some measurand, if 𝐶01 increments by a particular value, 𝐶02 will decrement by the same value. So we can represent 𝐶01 as say 𝐶01 plus or minus delta C, and 𝐶02 as 𝐶02 minus or plus delta C. So where delta C represents the change in capacitance due to the measurand, and 𝐶01 and 𝐶02 are the offset capacitance possessed by those capacitors. So ideally, 𝐶01 and 𝐶02 will be equal. So there are many applications where such type of sensors are used, like for example in linear displacement measurement, inclination measurement, shear force measurement, etc. So there are many applications, and the main advantages of capacitive sensor is its higher resolution, sensitivity, and low power consumption. Okay, so there are a variety of measurement circuits available, and there are many challenges for each of these measurement circuits. So we'll discuss few challenges of the existing measurement schemes. So one is the large measurement time. There are few circuits which has a lower measurement time, but in effect there is error too. So the other challenge is the non-linearity error due to the open loop configuration in most of this architecture. And third challenge is the challenge that highlighted here is the effect of mismatch between the offset capacitance. So ideally, as mentioned earlier, both the capacitors will be having offset capacitance which is equal, but in most of the existing measurement schemes, it is assumed to be equal. But due to the manufacturing defects, or if say by due to connecting wires or its design, definitely the capacitors, offset capacitance won't be equal. It will be different. So definitely, if we are using some existing measurement schemes, it will create error. So that is one challenge, how to overcome that. And the other challenge is like the presence of parasitic capacitance. So most of these measurement schemes are sensitive to the parasitic capacitance. So in general, we can say like existing architectures, the digital output of this existing architecture depends on this mismatch in offset capacitance as well as the parasitic capacitance. So based on this, we propose a novel capacitance-to-time converter. So this is the proposed block diagram or proposed architecture. It's a capacitance-to-time converter whose output is a pulse width modulated output, and the on time period of that pulse will be proportional to the change in capacitance delta C. Okay, and I have developed the circuit in such a way that the output is independent of this offset mismatch and the parasitic capacitance. So that is a novelty of my proposed architecture. It implements a closed loop circuit, and as such, it is independent of non-linearity errors, and it eliminates the effect of mismatch between the offset capacitance through an automatic offset-mismatch nullification process. And this it is a high-speed measurement circuit, and the output is totally independent of the parasitic capacitance. So this is a proposed signal conditioning circuit. It basically consists of two blocks. One is the triangle wave generator, and the other is converter. So let us see how it works. So the first one is the triangle wave generator. It consists of basically an integrator and a comparator circuit. The switches S1 and S2 is controlled by the output of this comparator in such a way that we will get the triangle wave. And the triangle wave will have a time period t. And for ease of understanding, we just divide the entire time period as 4 phases: P1, P2, P3, and P4. So this triangle wave is given as input to the converter. Okay, so the converter consists of the converter contains that an integrator formed by the op-amp OA2 and CF, to which we connect the sensor DCS CX1 CX2 through the switches S3 and S4. It has also a reference capacitor CS, and it forms one of the feedback network and has a logic circuit here. Okay, so we'll see how it works. So we'll assume initially as the capacitors are ideal, that is it has 𝐶01 and 𝐶02 to be equal, and say delta C is equal to 0. Okay, so I also meanwhile let us assume that there is no CS, that is there is no reference capacitance. So during the process, like say during the phase P1, the switch S3 and S4 will be switched to position 1, which means CX2 is not connected to the integrator, while CX1 is connected to the integrator, and that phase P1 forms the half of the positive slope of the triangle wave. So as we know, the current through CX1 will be like differential of it will be like C dV by dt. So it differentiates the voltage, and that will be the current. So in effect, the current through the CX1 flowing into the integrator will be a square pulse, and as shown there, the amplitude will be proportional to CX1 during and that will be integrated by that op amp and capacitor CF, that is shown as V02. So during the P2 and P3 phase, the switches S3 and S4 will be connected to 0 and 1. That is the entire sensor is disconnected from the circuit. So there won't be any current IE. IX1, IX2 will be 0, IE will be 0. There won't be any current. Hence the output voltage at V02 will be held constant. And during phase P4, the CX2 will be connected. And we can see like during that phase, the input triangle wave, it is having in negative slope. So definitely the amplitude will be negative. Current will be having opposite direction. So that current Ix2 is again integrated by the integrator. Now, if CX1 and CX2 are equal, that is 𝐶01 and 𝐶02 equal, and delta C is equal to 0, then the net current Ix1 and Ix1 minus Ix2 will be equal to 0. So the voltage V02 will be again will be at 0 itself. So so when the process goes on, the voltage V02 will be at 0. Now what happens when delta C is not equal to 0? So when delta C is not equal to 0, this current Ix1 and Ix2 won't be equal. So definitely the voltage V02 will increment either in positive or negative direction. So as shown here. So and ideally it will go to some large value. So in order to compensate that, we introduce this capacitor CS. So it just like a feedback, and it is connected to the integrator through the switch S5, and that is controlled by the comparator circuit OC3, and OC3 compares the triangle wave and the output of the integrator. Okay, so suppose again we'll assume 𝐶01 and 𝐶02 equal, delta C equal to 0. So what happens is V02 is at 0. So the switch S5 will be connected to OA2 through the switch S5 for say time period T1 during the positive slope, and for time period T2 during the negative slope. That is controlled by the comparator OC3. So whenever the voltage is V02 is 0, that both time period T1 and T2 will be equal, which means the current IS through the CS will be in effect the sum of that current will be 0. So there won't be any change in V02. Now suppose delta C is not equal to 0. So Ix1 and due to Ix1 and Ix2, Ix1 minus Ix2 will be the error current IE. So the voltage V02 will either increment in positive or negative direction. So that will change the V02, and to compensate that, we should adjust T1 and T2, right? So if the voltage increments above, the T1 will be broadened and T2 will be shortened. And in similar way, if it is going down, it will be changed. So that will be controlled by VOC3. So whenever V02 increases, the time period T1 will increase and T2 will decrease. And whenever the V02 decreases, T1 will shorten and T2 will be broaden. So what happens is the net current through CS IS will be won't be equal to 0. Net current IS won't be equal to 0 during entire period. So at a particular point, this current IS will compensate Ix1 minus Ix2. So at a particular point of V02, the error current IE will be made 0. So at that point, the voltage V02 will settle. So the output voltage will be somewhat like this. It will settle to a particular point. That is, the net change in the voltage at V02 during each time period will be equal to 0. So at that point, we can measure what is the change in delta C with respect to CS. So whenever it settles, we can write the change in voltage V02 during each period as like this. So it's a relation between CS and delta C. So whenever it settles, V02 will be delta V02 will be 0. So we can say delta C is proportional to T2 minus T1. T2 and T1 is the time period to which CS is connected to the integrator. Okay, so always T1 and T2 is kept in such a way that T1 plus T2 is equal to T by 2. So in general, we can write delta C as equal to 4S into T by 4 minus T1 by T, where CS is constant, T is constant, only T1 should be known. So we can get that value T by 4 minus T1 through this logic circuit. So this logic circuit is basically to get a pulse output whose time period is equal to T by 4 minus T1. So in general, the above circuit will have a feedback operation, and it will settle to a particular value. And in order to get the T by 4 minus T1 time period, we have included such a logic circuit. So output of this logic circuit will be a pulse train whose time period of the pulse will be equal to T by 4 minus T1. So the output, we just need to check what is output V0, and the delta C will be proportional to T0. So again, CS T is constant, so the output delta is linearly changes with T0. So these are basic functionality of the circuit. So say we'll see what happens when 𝐶01 and 𝐶02 are not equal. So here in the proposed signal conditioning circuit, it implements an automatic offset mismatch nullification process. So this process is carried out by the CLU. So what happens is, like whenever we connect a new sensor, a differential type capacitive sensor, the CLU will initially set CS aside, like it won't connect the CS to the circuit, and it will check the output voltage V02. So if 𝐶01 and 𝐶02 are not equal, the V02 will increment in positive or negative direction. So what happens is, like CLU will automatically adjust the on time or of CX1 and CX2 to the integrator such a way that like the output will again settle. So for example, if the voltage is incrementing, it will shift T3 and T4 accordingly, and always it sets T3 plus T4 equal to T by 2. So at a particular point, the voltage will settle, and whenever it settles, CLU again set CS to the circuit, and it will again come back to 0. So so initially itself, it will compensate the effect of mismatch. So this is how automatic nullification process works. And if you analyze it, we'll get again delta C proportional to T0. Okay, so that is the basic functionality of the circuit. The prototype was developed in the institute. So this was a prototype. It was done on a breadboard. And it was tested for a range of minus 180 to 180 picofarad. And we got a full-scale linearity error less than 0.3%. And in order to check the efficacy of AOFN process, we tested the mismatch, like we varied the mismatch between the offset capacitance from 0 to 200 picofarad. So it's a huge mismatch. And even in that mismatch, we got a worst case error less than 0.29%. So it is much efficient compared to the existing architecture. And the insensitivity to the parasitic capacitance also tested, and we got a worst case error much less than 0.149%. So it's again negligible. So comparing to the existing architecture, it has a high update rate, like 2 milliseconds, and automatically eliminates the effect of mismatch between the offset capacitance. And there is no extra error correcting circuit required. So basically the CLU itself will control the on time of both CX1 and CX3. So there is no separate error correcting circuit is not required there. So that is the advantage. So let me summarize the work. So there are many measurement circuits, but in the proposed circuit, we have overcome some of the challenges, like the offset mismatch nullification, and it implements a fast measurement circuit whose output is a pulse width modulated output, and it's the time period of the pulse width of the pulse is proportional to the change in capacitance delta C, and it was developed in the institute, and we could get a good performance. So thank you.